The different pieces of section 8.2 all have to do with homogeneous linear systems, but you can also have non-homogeneous systems. And in a general sense, the way that you would solve a non-homogeneous system is kind of like how you solve a non-homogeneous equation. You can see it here. You get a complementary solution and a particular solution. So what we were doing in section 8.2, those end up being complementary solutions in this context here where we have a non-homogeneous system. So then how do you get the particular solution? Well, that's a little bit different. It's this down here where I think the first natural question would be, what's phi? Well, what phi is you can form it based off of the complementary solution. Basically, it's a matrix where you have to have independent solutions to the homogeneous system or the corresponding homogeneous system in the columns. So that's what you end up doing. So like it says here, it looks like the complementary solution, but if you just left off the arbitrary constants, and I guess if you weren't adding them together. So that way they end up being in distinct columns. It does kind of look like that. And then the f is just the part that makes it non-homogeneous. So if this is the form of the non-homogeneous system where the f is added on here at the end, so it's not part of this here, so the a times x part, that's the part that makes it non-homogeneous, and that's just what goes in there. So you don't really have to find f. You do have to do a little bit of work to get phi inverse, though, and we'll see that on the next page. But speaking of which, if you have a 2x2 matrix, and this is just another linear algebra thing, but it's worth it for 2x2 matrices, and it's going to be worth it in this example because we're going to have one. You can see it right there. There is another way to get the inverse of a 2x2 matrix besides augmenting the matrix with the identity matrix and then doing row operations to get the identity matrix on the left and then the inverse is on the right. That's still going to work. But with a 2x2, you can also do this, where if A is just some generic 2x2 matrix, so A, B, C, D, just some numbers or some entries, then A inverse, it's 1 over the determinant of A times this matrix over here, which kind of looks like A, except that the little a, little d have been interchanged, and then B and C are negated. So that for a 2x2 matrix is usually the faster way of getting the inverse. You don't have to do it that way, but a lot of times it is a little quicker. So let's say we want to get the general solution of this right here, this non-homogeneous system. I already did the complementary solution. It ends up working out nicely because you end up with 2 distinct real eigenvalues, so they each give you a single eigenvector. And so then there's the complementary solution right there, right? So k1 goes with lambda 1, right? The 1, -4 vector is going with the -3 with that eigenvalue. And then I guess by process of elimination, those are going together as well. So k2 is going together with lambda 2. Okay, fine. There's our complementary solution. Now we've got to get the particular. And I stuck the final answer in here. So here's the complementary solution, the first 2 terms, and the last 2 terms are the particular. But the important thing, I guess, would really be how you get the particular solution. So f, you don't really have to do anything to get it. It's just tacked onto the end up there, right? There's f, that vector. And then the way that you get phi, it comes out of here. So you could ignore the C1 and the C2 and just say, I want 2 linearly independent solutions to the corresponding complementary, or the corresponding homogeneous system, right? The one that the complementary solution would be a solution of. All right, so if you leave that off and then multiply this out, then one vector in phi would be 1e to the -3t, and then underneath -4e to the -3t. And if I scroll down, there it is, right? It's this first column right here. If I go back up, the second one, so the other solution that would be an independent one, you use this piece, right? You use this second term of the complementary solution, and if you multiply 1 by e to the 2t, you get e to the 2t, right? So that vector is just going to be e to the 2t in both entries. So e to the 2t, e to the 2t, which is right there. So you just make a matrix where those independent solutions are going to be the 2 columns. So that's what phi is. And then we have to get its inverse. So there's the determinant, because I'm going to use that method on the first page for how to get the inverse. So I'm going to need the determinant. And if you get it, it ends up being 5e to the -t. And then here's phi inverse. It's going to be 1 over the determinant times, and then if you look at these entries compared to up here, the ones on the diagonal that go from the upper left to lower right are interchanged compared to up here, and then on the other diagonal, so upper right to lower left, those are negated. And then I just rewrote 1 over 5 e to the negative t as e to the t over 5 just to make the multiplication a little bit easier. Because to multiply this one term by this matrix, what you have to do is multiply that term by every entry in the matrix. So like that's where the 1/5 e to the 3t comes from. So e to the 2t times e to the t would be e to the 3t, and then you're also multiplying by 1/5, right? And if you do that to all 4 entries in the matrix, you just multiply them by e to the t over 5. Then the thing that we're supposed to integrate, phi inverse times f. Well, we just got phi inverse, and there's f, so we're going to have to multiply these out, which should give us a column vector ultimately, and that's what we get here, right? Because it's going to be this row times that column, and then this row times that column, right? So you end up here, and then we've got to integrate these. So I guess this part is just matrix multiplication, right? That's more linear algebra than anything else, getting from there to there, right? So that top row, 1/5 e to the 3t times e to the negative 2t will give you that term. And then negative 1/5 e to the 3t times negative 2 e to the t would give you that term. And then you do the same thing for the other row. But then you end up here, and to integrate a matrix, you just have to integrate each entry. So integrating that first one, you integrate 1/5 e to the t, that's just 1/5 e to the t. And then the other part of that sum, if you integrate 2/5 e to the 4t, it's going to be that multiplied by 1/4. So you multiply 2/5 by 1/4, that's 2/20 or 1/10. And then you do the same thing for this other entry down here on the bottom. You integrate that, you end up here, right? Term by term, just like the top one. So then you got to multiply that by phi, or I guess really multiply phi by that, right? Since matrix multiplication doesn't commute. All right, so we get down here, and we already have this integral. So here's phi, and then here's the thing that we just got, that integral. And then if you multiply those together, so I guess then for the top row down here, you'd have e to the negative 3t times this, and then plus e to the 2t times this down here, and you end up there. Then bottom row, 4e to the negative 3t times this up here, plus e to the 2t times this down there. And so each of these ends up with 4 terms, where we end up being able to simplify quite a bit, because in both cases you have a couple of terms that add out, and then the other 2 are like terms that you can combine. And eventually what you end up with is that x sub p, your particular solution, it's the column vector where the first entry is 1/2 e to the t, which you get from the 1/10 plus 2/5 e to the t. And then on the bottom, the second entry, you get negative e to the negative 2t, because down here you got this one and this one adding out, but then negative 4/5 minus 1/5 is negative 1 e to the negative 2t. Or if you want to break that up, you can write it as one part of x sub p being the vector multiplied by e to the t, and then another part being a vector multiplied by e to the negative 2t. So we can write it like that, and that is, I think, the more conventional way of writing out a final solution for this sort of thing. So that's how you end up with that answer, and that is what you get at the end of the first page, right? The last 2 terms look like this. I think I may have rewritten it a little bit differently. I think I had like a minus here, and then it's 0, 1, but same thing, right? You're going to end up in the same spot. So getting x sub p here when it's matrices, when it's non-homogeneous systems, it's a little bit different, right? It's more linear algebra stuff, right? Matrix multiplication, getting the inverse of a matrix, that kind of thing. But there is a way to do it. So for completeness' sake, it makes sense to get this in here that you could also have a non-homogeneous system, and there is a way to do variation of parameters.